Hello, 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 hello. Am I audible? Okay, so today there's a bit of a technical issue. My internet connection is not good, so have connected using mobile data. My Wi-Fi is not working, so there might be my voice might be choppy. Hopefully, data works fine. I'm not sure about when my internet connection will come back, so we'll make do with what you have. Okay, this week you studied Viterbi, no, not Viterbi, BCJR algorithm and all, but the problems given for this week are mostly related to topics covered last week, actually. So I think the way the assignments are designed, some of the problems are from 1 week earlier. They're related to topics covered 1 week earlier, and some of the problems are from this week. Or maybe it's because they had problem solving session videos from the professor himself. So these problems, assignment problems, are related to the problems that he solved. Not sure which of the two it is, but uh, as usual, there will be 10 questions. And since today there's some problem, I'll try to get this over with as fast as possible. All right, today is already week five, six, seven, eight, only 4 weeks left. This is about the time when students stop attending, so I won't wait for any more time. I'll start right away. And whoever wants it can just attend the Tuesday session or watch the recording, which will be uploaded on YouTube. Like, first question, which of the following statements are false? First statement is BCJR algorithm can be applied to both linear block codes and convolutional codes. So that's a correct statement. It can be applied to all linear codes, and convolutional codes are also linear. Uh, you can go and check in the lecture that that statement is true. Yeah, that's the first question, but well, now you know the answer. So take it as a bonus for attending the problem solving session, I guess. Second option, decoding of convolutional codes using BCJR algorithm minimizes the bit error probability. That's a true statement. Third option is Viterbi decoding of convolutional codes minimizes the bit error rate. Minimizes the bit error rate. This is not true. It doesn't. It will. It is a maximum likelihood estimator. It's based on maximum likelihood. So it will find the most likely path, the path that maximizes the likelihood, but it won't also minimize the bit error rate. The Yeah, it's an efficient decoding algorithm, so it's useful. But yeah, you can see in the lecture, it doesn't minimize the bit error rate. And Viterbi, the BCJR can be used for linear and convolutional codes. Viterbi is only for convolutional codes. That's one disadvantage. So that's the false statement. And final is none of these, but we did find a false statement. So answer is option C. Okay, question two. Consider the 3 to 3 systematic feed forward encoder with G12 of D is equal to 1 plus D square plus D cube. G22 of D is 1 plus D cube. How many delay elements are required in the controller canonical form realization of the convolutional encoder, delay elements, memory elements, whatever it is, a buffer. So this you can answer directly. Uh, it's okay. First, NKM is 3 to 3. There are two inputs, three outputs. Memory order is 3. So we are using up to three previous inputs. So in the controller canonical form, there will be K shift registers, one shift register for each of the K input sequences. And a shift register, so if your output uses all three delayed elements, so here you can see from G1 and G2, you're using one D square, D cube, and D term. So you are using all the delayed elements, delayed. whatever is stored. So each of them will have, and each of them is going up to d cube. So so here this G1 that corresponds to the first input and G2 corresponds to the second input. So for both inputs, you need three delay elements. So both of them have one shift register, and each shift register has three memory elements. So the total number of memory elements will be six, and you can write that directly. The realization of that circuit. So in the lecture, you had seen that for a controller canonical form realization, you have something of this form, and F0, F1. So the delayed, whatever is stored in the buffer is either added to the adder. So this F1 here, we are using binary, so it will be 0 or 1. If it's 0, that means there's no connection. If it's a 1, that means there is a connection. It's like your PAL, PLA circuit, where you can blow a fuse to form a connection or destroy a connection. So it's something like that. So each of these F1, F0, F1 up to Fm can be 0 or 1 in the binary case, and if it's 0, the connection doesn't exist. If it's 1, you simply directly add the output of the buffer behind it. That would, and there will be feedback elements also, QM, this will be Q2, Q1. If you are allowing feedback, but here in our question, it's a systematic feed forward encoder, so there's no feedback. So we can ignore the feedback elements. We can assume that all of the QAs are zero. So this will be for one of the inputs, and there will be a similar structure for the other input also. And then that will be added, those two will be added. The outputs corresponding to each of the inputs will be added. And if you have one input and one output, then the G of D that you get from this type of circuit will be F0 plus F1D plus etc. up to Fm minus 1 Dm minus 1 plus Fm d power m. If we compare it with what our generators are doing, G1 2 of D is 1 plus D square plus D cube. So F0 is 1, F1 is 0, F2 is 1, and F3 is 1, and M is only 3 here, so it goes up to F3. Similarly, for G1 1 of D, you have 1 plus D plus D cube. So F0 is 1, F1 is 1, F2 is 0, and F3 is 1. So for the first circuit, you'll have U1 here, right? Corresponding to that, G12 of D will give you the output. So F0 is 1, that means the connection here. F1 is 0, that means this connection is eliminated. And there'll be one more, I guess. there will be three elements only. So we look this, and this will be your F2. So F2 is 1, so there will be a connection, and F3 is also 1, so there will be a connection here. So this will give you the connection you need to give for the first input sequence. For the second input sequence, for the second input sequence, F0 is 1, F1 is 1, so there will be a connection here. F2 is 0, so this connection won't be there. So this will be the connections that you do for the second input sequence, U2, and then you add both of these, the connections for F1 and connections for F2. So in the end, to this adder, you'll have another part coming from U1, the one we had previously done. Okay, now another thing you have to note is that it is a systematic encoder. Systematic encoder is similar to the systematic generator matrix that you had for linear block codes, where you'll have a generator matrix of the form IEP. So some of the code word bits will be the message bits directly taken. So here also this U1 is directly taken as one of the code word bits. It will be V0. The second input sequence is also taken directly as V1, and the third code word for that third code word you have these two generators G1 and G2. So instead of writing these connections at the top, I'll just write it in a different way, but it's the same connections in the end. So you have U1, that is dU1, this is d square U1, this is d cube U1. So first generator has 1 plus d square plus d cube. So 1 means you take the output directly, input directly. D square is this one here, d cube is this. And from the second input sequence, you have another set of memory elements U2, dU2, d square U2, and d cube U2. The second generator is 1 plus d cube. So U2 is directed directly, that's the 1. Then you have d and d cube. And these two in the end are added together to give you V2. So that's your controller canonical form of the convolutional encoder. And as you can see, you have 6 memory elements. So in the controller canonical form, there is a register. A register is just a set of memory elements for each of the inputs. And since the outputs are using all 3 of the memory elements for each of the inputs, so there will be 3 memory elements per input. So there will be two shift registers of size 3, and the output will be written as the sum of the delayed versions of the input and the input itself for both the inputs. This is it's systematic. The inputs are also directly given as the outputs. So you have two more. If there are k inputs, then there will be k outputs which are directly given. That's the controller canonical form. We had one more canonical form. That will be question 3. In question 2, how many delay elements are required in the observer canonical form realization of the convolutional encoder? This is a different form. In the end, you're realizing the same function. It's the same convolutional encoder. So, since this is also systematic, similar to the previous question, you will have one code word, one bit of the code word directly as one of the inputs. The other, it will be U2. Now again, you have a V3. No, not a V3, a V2. So the realization for observational observer canonical form is a bit different. If it's only feed forward, then if you have an input here, I'm assuming there's only one input, so you can pass that input to one delay element. So Fn minus 1, you can add that before passing it through another delay element. Then you can scale it by Fm minus 2 and pass it and add it to the output of the previous delay element before giving it to the next one. You can keep going. Finally, you'll have F0 times U plus here you'll have some delay element. Those two things will be added and that will be your output. The generator, the transform domain will be of the form F0 plus F1D plus etc. plus Fm minus 1 dm minus 1 plus Fm d power m. Since m is equal to 3 here, g of d will be F0 plus F1d plus F2d square plus F3 d cube. You'll have for G12, you'll have same as the previous question. We had 1 plus d square plus d cube. So for G12, you have F0 is 1, F1 is 0, F2 is 1, and F3 is 1. And for G22, you have F0 is 1, F1 is 1, F2 is 0, F3 is 1. The Fs are the same, but here you are adding the input before a delay element. If your FM is 1, or if FM is bottom, this connection won't exist, so you are not adding it to the delay element. So the way you would write this is there is one register for each of the outputs, but V0 and V1 are uh, directly taken as since it's systematic. So only for V2 you need a combination of the inputs and their uh, previous bits of the input and the current bit of the input. So there will be one shift register for V2 and the size of the shift register will be 3. So there will be 3 delay elements. So now if Fm is 1, then there will be a connection Fm, here M is 3, so F3. If F3 is 1, there will be a connection from the input to the adder of the first delay element. Right? You can see Fm, this is F3. So if F3 is 1, to the first delay element, you are directly giving your U. And you can see that F3 is 1 for both inputs. So both these inputs will add to this first adder. So there's a connection from U1 to the first adder, and there's a connection from U2 to the first adder. Next is Fm minus 1, which is F2. If F2 is 1, there's a connection from the input to the second adder of the second delay element. F2 is 1 only for the input, first input. F2 is 0 for the second input. So U2 shouldn't be connected to the second adder. U1 should be connected to the second adder. So you're taking only U1 and adding it before the second delay element. Next is, so this will be F1 here. So if F1 is 1 only for the second input, so to the third delay element, to the third adder, you're only adding U2. And finally, F0 is 1 for both of the inputs. So to the final adder, we will add both of them. So essentially what's happening here is let's check only for one of the inputs. So you're adding U of 1 here, that is delayed here. This is a delay element. U1 is delayed and the output here is D U of 1. Again, you are adding U of 1 here. So the input to the second delay element is U of 1 plus D U of 1. So the second element will delay this, D times this, the input. That will what be there here, right? D U of 1 plus D U of 1. Again, so the first input is not being added to this third element, third adder. So that is passed to the uh, third delay element. Third delay element will delay this again and send it to the final adder. So in the end, what you get is d square u of 1 plus d cube u of 1. Finally, here to the final adder, we are adding u of 1. This is u of 1. So the final output is u of 1 plus d square u of 1 plus d cube u of 1. That's what we wanted, right? G1 of 2 is 1 plus d square plus d cube. So V of 2 is u convolved with g, u multiplied with g in the transform domain. So it's u of 1 plus u of 1 d square plus u of 1 d cube. But that's only for the first input. You're also adding the second input in each of these places. We'll see what happens to the second input next. So you get the second input here, u of 2. It passes through a delay element and becomes du of 2. To that, you are again adding u of, no, you are not adding u of 2 here. If I write like this, if I mark a big dot, that means there is a connection. Here, there's no dot, so there's no connection with u2 there. So I'm not adding u2 at this stage. I'm passing du of 2 to the next delay element, so you get d square u of 2. Now I'm adding u of 2 again, so I get u of 2 plus d square u of 2. That is what is given here at the adder. Now again at this point you are adding u of 2. So finally we get, sorry, there was, we had d square u of 2 here. We added u of 2 to that. You get d square u of 2 plus u of 2, and then it passes through this delay element. So it's d cube u of 2 plus du of 2. So that here you are adding u of 2. So one more u of 2 is added. Then you got u of 2 plus du of 2 plus d cube u of 2. That's what we wanted. 1 plus d plus d cube. Okay, so that's the difference between the observer canonical form realization and the controller canonical form realization. In the controller canonical form, you'll have delayed versions of all the inputs, which will be stored in the uh, registers, and then you'll take those delayed versions, whichever you want, and add them and give that as the output. In the observer canonical form, you have adders in the memory elements. So to the input of the memory element, you can add your input information bit, or you might leave it as it is. So there will be just one set of adders with one set of memory elements with internal adders. Here you don't have that. So the input to the next adder, next um, flip flop, or usually memory elements will be flip flops. So the input to the next flip flop is just the output of the previous flip flop, right? You don't add anything else to the input of a flip flop. You can only take the output of the flip-flop and feed it to the output code word bit. But in the observer form, you can add to the input of the flip-flop itself. But you can't take away any of the outputs of the flip-flop directly. You can only take the output from the final flip-flop. Here you can see you're only taking from the final flip-flop. You can't use any of the outputs from the previous flip-flops directly. But in the end, they will realize the same code words, I guess. It's the same generator matrix. So why would you have two different forms like this? You can see if you have smaller number of inputs but a large number of output bits, then you can store, you need only k shift registers, right? For k inputs. If k is less than n, then you can use this form. But if n is less than k, there's one shift register for each output. So if there are lesser number of outputs, you can use this observer realization and you will need lesser memory elements. That's one benefit. I don't remember any other benefits, but there are probably other benefits too. Okay, so we saw two different realizations of the same generator. We'll go to the next question. Question 4. Consider the 312 non-systematic feed forward encoder with g of d equal to 1 plus d, 1 plus d square, 1 plus d plus d square. And information sequence is encoded using this convolutional encoder and transmitted over a binary symmetric channel with crossover probability p is equal to pi into 10 power of minus 2. What will be the upper bound on event error probability? Okay, so they have given g of d. The first element of g of t is 1 plus t. So u plus ul at time L, the output, one of the outputs will be ul plus ul minus 1. Second term is 1 plus d square. You will have ul plus ul minus 2. Third term is 1 plus d square. We will have ul plus ul minus 1 plus ul minus 2. So the realization of this encoder is like this. You have one bit. It's a 312 encoder. So this is NKM. K is 1. There is only one information bit at a time. Three output bits. N is 3. And memory order is 2. So there will be two memory elements. So this is a delay element, this is a delay element. You'll get U, here you'll have du, this will be d square u. So first output V0 is 1 plus d. So this is 1 u, so it's 1 plus d. Second output is 1 plus d square. It is 1 plus d square. That's the second output. Final output is 1 plus d square. So u plus du plus d square u. That will be your encoder. From that, you write the state table, input present state, next state, and the output. So present state can be state is nothing but what is stored in the memory elements. In each of the memory elements, you might be either you're storing only bits here. So you might be storing a 0 or a 1. If there are two memory elements, you might be storing 0, 0, 0, 1, 1, 0, or 1, 1. The contents of the memory elements will give you the state. So you might be in the state 0, 0, or you might be in present state 0, 1. Present state might be 1, 0, or 1, 1. And when you are in a particular state, your input bit might be 0 or 1. So it can be 0 or 1. So if you're in state 0, 0 and the input is 0, what will be the next state? So from the uh, diagram here, you will have to calculate that, right, for each of V0, V1, and V2. And of course, the next state can be easily found because input bit is pushed to the first memory element. Output, the contents of the first memory element are pushed to the second memory element. So in terms of this table, this bit will come here, and this bit will go here, and this bit is discarded. So in state 0, 0, if input is 0, you will be in state 0, 0 itself. If state 0, 0, if input is 1, you will go to state 1, 0. Similarly, from 0, 1, if input is 0, you'll go to 0, 0. If input is 1, you'll go to 1, 0. From 1, 0, you'll go to 0, 1 or 1, 1. From 1, 1, you'll go to 0, 1 or 1, 1. And when these transitions happen, you will have to calculate V0, V1, V2 using this diagram or the formula. And you do that on your own. I'll just give you the answer directly. You can check and verify if these values are correct. The output here will be 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0. We did these type of questions last session, so I won't do all the steps again. Okay. Once you have this state table, you can write the state diagram. State 0, 0. I'll call the state 0, 0 S0. Okay, S0 is the state 0, 0. S1 is the state 1, 0. S2 is the state 1, 1. And S3 is the state. Sorry, that's not the convention. S0 is 0, 0. We'll use S1 to denote the state 0, 1. S2 to denote the state 1, 0. And S3 to denote the state 1, 1. So we then state S0, S2, S1, S3. So from 0, 0, that is state S0, you can go to S0 or S2 with output 0, 0, 0 or 1, 1, 1. When the input is 0, output will be 0, 0, 0, and you'll go to next state 0, 0. When input is 1 and present state is 0, 0, you'll go to next state 1, 0 with output 1, 1, 1. So that will be written in the state diagram in the following way. So from state S0, you can go back to S0. If your input is 0, you'll draw a slash and write the output corresponding to that transition. Similarly, if the input is 1 when you're in state S0, your output will be 1, 1, 1, and the next state will be S2. So that's how you draw the state diagram from the table. If you fill up the rest of the transitions, this is the form of diagram that you get. We did several questions similar to this in the last problem solving session. So if you have doubts, you can go back and check that. All right. 1 slash 0, 1, 0, 0 slash 1, 1, 0, 1 slash 1, 0, 0, and 0 slash 1, 0, 1. Finally, 0 slash 0, 1, 1. So you get the state diagram, state transition diagram, and then you write the modified state diagram from that. Again, we did this a lot of times last class, and professor also had a few problem solving sessions with these type of problems. So if people are still unfamiliar, what we are doing is this 0 back to 0, we are splitting it in two. So writing from S0 all the ways you can go back to S0. So from S0 you can go to S2, then from S2 you can go to S3 or S1. S1, go to S3 or S1. From S3 you can go to S1 or you can stay in S3 itself. From S1 you can go back to S0. Now we'll write labels on these branches, and label will be x to the power something. Oh, hello, I'm losing my internet connection constantly, so there might be delays in the display. Sorry for that. Okay, now the so the weight on a branch will be x to the power something. Let's say I. This I is the number of ones in the output you get when you do that state transition. So here you are transitioning from state S0 to S2. So here in the diagram, if you check from S0 to S2, when you are going from S0 to S2, the output is 1, 1, 1, which has three ones. So the weight is 3. You will write that as the power of x. So write that weight of that branch as x3. Similarly, from S3 to S3, for this, the output is 0, 0, 1, which has a single 1. So the weight on that branch should be a 1. We'll write that as a power of x. We'll write that as x power 1, which is nothing but x. So I'll write that directly as x. So in this way, you write the weights on each of the branches. I'll write down all the weights. You can check this yourself later. If you still have doubts, you can go and see previous week's problem solving sessions. Okay, I have filled up the weights. It will take some time to come up on your screen. All right. So once we have filled up the weights, we'll write down all the loops and the gains in a loop. So there are three loops in the circuit. From S3, you can go to S3. That's one loop. The weight of that loop is X. The second loop, from S2, you can go to S1 and come back to S2. The weight on that is X square times X. X square into X, which is X cube. The third loop is from S2, you go to S3, then to S1, then come back to S2. Weight there is X, X square, and X square. So the product of those three will be X power 5. C3 is, sorry, it's go here in this part. So the gain is X. You go here in this path, gain is X square. Then you go here. You can't go this way. That's a one-sided arrow. So here the gain is X. So the total gain will be X into X square into X, which is X power 4. Okay. Now delta is, okay, we still have to find the gains, product of gains along non-touching loops. So next, these are three loops. Next, we have to see which of these three loops are not touching each other. So we say two loops are touching each other if there is at least one node common to them. But if you see the loop from S3 to going back to S3 and the loop S2 to S1 to S2, there are no nodes common to both of them. So they are non-touching loops, and those two are the only non-touching loops. You consider this loop and this loop, they have S3 in common. And if you consider this loop and this loop, they have S1 and S2 in common. So we say those loops are touching. But if you check this loop and this loop, there is no node in common. Those two are non-touching loops. You have to write the sum of products of non-touching loops. Since there's only one pair of non-touching loops, you have there's no sum. You just have the product of those loops. So loops S3, S3 and S2, S1, S2 are non-touching. So gain is C1, C2, which is X into X cube, which is X power 4. Now, if you had three loops which are non-touching, four loops which are non-touching, you would again have to find the sum of products of those loops, and then you would add or subtract depending on the pattern. So here you would do delta is 1, so you have a positive in the first term, So plus 1. Then you have minus sum of gains of individual loops. And you have a plus sum of product of the gains of non-touching loops. So you have C1, C2 here. You might have had other things also. If it was a different diagram, you might have C3, C4, something like that. That's it. And then minus the sum of products of three non-touching loops and so on. So it would alternate in plus minus fashion. But here we have only these terms, and there will be 1 minus x plus x cube plus x power 4 plus x power 4, which is nothing but 1 minus x cube. Next, what we have to do, we have to check the forward paths. There are two forward paths. Path 1, you go from S0, then to S2, then S0, and back to S0. That is this forward path. S0, S2, S1, S0. So it's a forward path because you don't cross any of the nodes twice. You don't go back at any point. The gain along that path is product of the gains of the branches along that path. So you have x cube into x square into another x square. So that's x power 7. Part 2 is S0, S2, S3, S1, S0. That is this path. You go from here, 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 that way. And the gains are here you have x cube into x square into x square again. So the gain along that path is x power 8. F2 is x power 8. Then delta 1 is you do the same thing that you did for the calculating delta, but now for the ith path, you remove all the nodes in that path. So delta 1 is corresponding to path 1. We have to remove all the nodes in path 1. So you'll only be left with path 1 is S0, S2, S1, S0. So you'll only be left with S3 that has an X like this. So you find the delta of this path. For that, you have to do 1 minus sum of the loop gains of that path. There's only one loop. So gain is X. So it will be 1 minus X plus sum of the products of non-touching loops. But there's just one loop, so there are no non-touching, for a pair of non-touching loops. So all the other terms will be 0. So in the end, delta 1 will be y minus x. Delta 2 is a similar thing, but in part 2 you include all the nodes. So you're going through S0, S2, S3, S1, S0. So you'll have to remove all those nodes, and if you remove all those nodes, there's no node left. So there won't be any loops. There are no nodes at all. So delta will be 1 minus something loop gains, but there are no loops, so it will just be 1. That way you get delta 1 and delta 2. And finally, once you have all of this, the weight enumerating function. Weight enumerating function, which is the actual useful stuff that we want to know. Last lecture and all, they were using t of x for this. It's the same thing, but they have used a different index. Don't be confused. Same thing as t of x, which is f1 delta 1 plus f2 delta 2 divided by delta. So f1 we had x power 7, delta 1 is 1 minus x, f2 we have x power 8, delta 2 is 1, divided by delta was 1 minus x cube. So it's 1 minus x cube. X power 7 minus x power 8 plus x power 8, which will be nothing but x power 7 divided by 1 minus x minus x cube. So we have this. Now we'll go back and see the question says what will be the upper bound on the event error probability. So what event error probability is and how do you find that? The formula for that was taught in the lecture, and I am taking this formula directly from the lecture. The event error probability is bounded by P of E is less than A of x, where x is 2 into root of P into 1 minus P. So this P is the crossover probability of the binary symmetric channel. So this is for the binary symmetric channel, and the value for P they have given is 5 into 10 power of minus 2. So you have to plug in the numbers. You can, I don't know if they'll let you use a calculator in the exam. Hopefully they do. So 2 into 5 into 10 power of minus 2. 5 into 10 power of minus 2 is nothing but 0.05 into, okay, there's a square root, into 1 minus 0.05 is nothing but 0.95. So you put that in a calculator and calculate the value, you'll get 0.4359. Okay, they'll definitely let you use a calculator for that, otherwise they won't ask. That's too ridiculous to do it by hand. And finally, you have to evaluate a of x at this point, which is, okay, this was x. So you have to evaluate a of x, this function, at that point. So you have to do p of e is less than x power 7, which is 0.4359 power 7 divided by 1 minus 0.4359, which is x, minus x cubed, 0.4359 cubed. So there's absolutely no way you can do that by hand. I use the calculator and I'll directly give you the answer. You can check yourself. It's always better to check all these answers yourself so that I am not made a mistake and you don't remember wrong stuff. So you'll get P of E is less than 0.062. Okay, so the event error probability is upper bounded by 0.062. That's the thing that they wanted, upper bound on event error probability. All right. So you have to do all that just for this. So finally, if it's an MCQ type of question, right? If you have in an exam or a test, try to solve the smaller problems first and then the bigger problems. Always try to do the easier problems first. Otherwise, you'll spend most of your time on this. Okay, if this is a 10 mark question, fine. But if it's just MCQ question with 1 mark, there's no point in doing this first. Unless you don't know the way to solve any other question. Okay, that was question 4. We'll try to move fast. Question 5 in Q4. What will be the upper bound on bit error probability? Okay, so it's very similar to the previous question, so I might as well copy everything and then do slight changes here. So give me a few seconds to copy the stuff. Okay, so what will be the upper bound on bit error probability? So now yeah, you have to follow the same procedure. The function you will get for P of E will be less than of some function B of x evaluated at x is equal to the same point. So the way you get that B of x is by doing a slight modification of this. Okay, so here what we put it as this modified state diagram was the weight of the output code word. So if my output in this state transition had two ones, I would write that as a power of x. I would write x square. So from S3 to S1, I have x square, right? That's you only took the number of bits in the output sequence. So now the sequence the function you want includes the input sequence also. So you write a power of w. Okay, there's only one input bit, right, in each of these transitions. So it will be either w power 0 or 1. So you write a w if your input bit in that transition was a 1. You don't write a w if the input bit was a 0. So that means take the same transition that I used now, S3 to S1. The input bit is 0 here. So in that transition, you leave it as it is. But suppose you take this transition S3 to S3 itself. The input bit is 1. So you add a W to the gain of that path. So it's the gain is not X, it's WX now. Similarly, S2 to S3, you have a 1 in the 1 as the input. So here you add a W. You do that for all the transitions where the input bit is a 1. That will give you an augmented modified state diagram. Right? You do that for all the state transitions. Here you can see only four of these transitions have an input bit of 1. Remaining transitions have an input bit of 0. So you have one here, 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 and here. So four of these branches will have a W added to it. Those four branches are going from S0 to S2, S1 to S2, S2 to S3, and S3 to S3. So both the branches coming into S2 and both the branches coming to S3 will have a W added to that branch. So we'll go here and add those W's. So add a W on both branches coming into S3 and both branches going into S2. And you repeat the procedure, whatever we did for the previous question, exactly the same way, except that now you have powers of W added. So this will be WX and next one will be WX square WX, which will give you Okay, let me see. Wait. Okay, this in the solutions they have. Okay, I'll solve it on my own. In the solutions, they are relabeled these loop numbers, so everything is a mess. We'll keep the same convention. T2 is from S2 you go to S1 and then go to S2. There's one W here, x squared Wx. It's just Wx cube. In the next loop, you have S2, S3, S1, S2, S2, S3, S1, and S2. You have two W's. Instead of X, you have Wx. So this is Wx, this is Wx. So you have W square x power 4. All right. Then non-touching loops, C1 times C2, W square x power 4, right? Finally, this will be 1 minus Wx cube plus W square x power 4 plus Wx plus W square x power 4. Okay. Wx, C1 is Wx, C2 is Wx cube, C3 is W square x power 4. So this W square x power 4 gets cancelled and you are left with 1 minus Wx minus Wx cube. And in the first forward path, if you go like this, you have only one W here. So that gets multiplied by W. Second forward path, you're going this way, and there are two W's in that path, this one and this one. So you'll get a W square, right? Similarly, this delta one will be 1 minus Wx because it was this gain, and delta 2 will be 1. Okay, you do the same thing again. So this function is called a of w comma x because we had this w also. W is just something that gives you information about the number of ones in your information input sequence. X is something that gives you information about the number of ones in your output sequence. And you might have one more called Z or something, which will be present in all the branches. That will give you sort of the weight of a path, so the number of branches in a path. But here we don't need that. We need only a of wx. This will be. Also, don't get confused. Like the previous lectures used t instead of a, and they used y instead of w. So the t in the previous lecture is the a in this lecture, and the y in the previous lecture is the w here. This is wx power 7 into 1 minus wx plus w square x power 8 divided by 1 minus wx minus wx power 3. If you simplify that, you'll get wx power 7 by 1 minus wx minus wx cube. Finally, we want this function b of x, which is 1 over k times the partial derivative of a, a of w comma x with respect to w evaluated at w is equal to 1. Give me a second. So this k is 1 for a question, right? It was a 312 encoder. K was 1. So k is 1 there. So we have the partial derivative of a of w comma x with respect to w evaluated w is equal to 1. Uh, you do the partial derivative and evaluate it yourself, okay? And check if you get x power 7 divided by 1 minus 2x plus x square minus 2x cube plus 2x power 4 plus x power 6. So you can check that. So now the bit error probability PB of E is upper bounded by B of x evaluated at x is equal to 2 times p root 1 root of p into 1 minus p. So we found x the previous question. X was 0.4359 from previous answer. So you evaluate b of x at that value and you will get pb of e is less than 0.0129. Okay, so you have completed 5 questions. Next questions are smaller than this. They won't take as much time. So does the feed forward encoder inverse exist for the encoder given by 1 plus d square and 1 plus d square plus d cube? So the answer is there are a few ways you can check. First thing you will check usually is what is the GCD of these two polynomials. So these are polynomials in the variable d. If you find d uncomfortable, you can replace them with x. First one will become 1 plus x square. Second one will become 1 plus x square plus x cube. So you have to find the greatest common divisor. If it is a power of x, then yes, there does exist an inverse for the encoder. An inverse exists, but it need not be feed forward. Uh, if the GCD is not a power effect, then there is some other condition. You can go back and check in the lecture. Uh, but the GCD of these two is 1. So how you check that? You have to No polynomial division that you study in school, and then there's an algorithm called Euclidean division algorithm. You can use that and find the GCD. So, okay, maybe I'll write it down. So first you divide the second term by the first term, d cube plus d square plus d plus 1. So this is d times. So d cube plus d. Subtract, you'll be left with d square plus 1 plus 1. Sorry, that's not right. I made a mistake somewhere. Wait, let me see. We'll come back to this later. There seems to be some mistake. We'll do that at the end. Otherwise, we'll just waste time. There's only half an hour left. Okay, so if this is g of d that we have, 1 plus d square, 1 plus d square plus d cubed. So g inverse of d, if it exists, then g of d times g inverse of d will be equal to d power l for some l. So here l is 0 in this question. So we have to find a matrix g of d, g inverse of d such that g of d times g inverse of d is equal to 1. And they have given the solution as g inverse of d is d over 1 plus d square and 1 over 1 plus d square. We'll come back to how we got that later. At least I'll give you the answer for now. Uh, but you can see that there's a denominator here, right? It's d over 1 plus d square, 1 over 1 plus d square. So you can't realize that using only feed forward encoder. So the question was, does the inverse exist for the encoder? Okay, I think the person who had previously solved this solved a different question and got the answer here, but the question is different. So I will skip this question totally. If we can, we'll come back to this at the end, or I will do this in the next session. I feel that the answer they have given is for a totally different question. Let's see if it's the case for the other questions also, or if the others are fine. So question 7, consider the 212 non-systematic feed-forward encoder. Okay, here, right, what I said earlier was right. So the inverse is like, will exist. One condition we can check is if the GCD of these two is a power of D. So you let's divide D square plus 1 D cube plus D square plus D plus 1 by D square plus 1 D times you'll get D cube plus D, right? You subtract that. Subtraction is just addition in mod 2, right? It's D cube plus D cube is 0 and D plus D is 0. So you'll be left with D square plus 1, you'll get plus 1 is D square plus 1, you'll get 0. So D square plus 1 actually divides 1 plus D square plus D cube. So the GCD of 1 plus D square and 1 plus D square plus D cube is 1 plus D square itself, because 1 plus D square divides it, which is not of the form D power L for any integer L. So the uh, okay, but we can't just conclude from this that inverse doesn't exist. We will have to check another condition given in the lecture. We'll do that later. But if you get this to be some power of L, then the inverse will exist. But the inverse need not be the feed forward encoder inverse. That's all I'll say for now. We'll come back to that later. Okay, question 7, we'll continue with that. Consider a 212 non-systematic feed forward encoder with G of D is equal to 1 plus D square, 1 plus D square. Its minimum delay feed forward inverse is given by uh, options are D square, 1 plus D square and D square, 1, 1 and does not exist. So one thing you can notice directly is 1 plus D square plus 1 plus D square is D, which is a power of L. So if you multiply 1 plus D square and 1 plus d square by 1 1, you will get 1 plus d square plus 1 plus d square. So it's mod 2, so these will cancel. So you'll get d, which is a power of L. So 1 1 is an inverse. We'll check the other options also. D square plus d power 4 plus 1 plus d square plus d power 4 plus d square plus d power plus d square plus d power 4 plus d power 6. So these two will cancel. You will be left with 1 plus d square d power 6. So that's not in the form of a power of d power L. Similarly, if you do for d square comma d square, you will get d square plus d power 4 plus d square plus d cube plus, sorry, this was d square plus d cube plus d power 5. So only those two cancel. And you are left with something that's not of the form d power n. And the second option, d square plus d power 4 plus d square plus d cube plus d power 5. Again, only d square is cancelled. So again, it's not a power of d. So I'm not sure if you can directly conclude from that if those two are not inverses. Let me check that. Again, we are running into the same problem. Okay, so for a rate 1 by n code, it's true. Okay, so let me write it here. For a for a rate r is equal to 1 by n code, a feed forward inverse exists if and only if GCD of G0 of D, G1 of D, etc. Gn minus 1 of D is equal to D power L, and G of D times G inverse of D will be equal to D power L, will be equal to the GCD. Okay, so that's the condition for the feed forward inverse to exist. All right. So in this question, we did find the GCD, right? 1 plus d square divides 1 plus d square plus d cube. It's d plus 1 times. So we'll get d times d square plus 1 is d cube plus d. 1 times d square plus 1 is 1 plus d square. So d plus 1 times d square plus 1 is 1 plus d square plus d cube. So 1 plus d square divides 1 plus d square plus d cube. That means the GCD of 1 plus and 1 plus d square also divides 1 plus d square. So 1 plus d square is the GCD of these two. So GCD of 1 plus d square and this other term is 1 plus d square, which is not of the form d power L for any integer L. And here it says this feed forward inverse exists if and only if it is of the form d power L. So for this question, this implies feed forward inverse does not exist. So the questions I am solving are actually from a previous year assignment. We do that so that they'll be similar in structure to your current year assignments. So it will be useful to you. That's why we do this. And the previous year solutions are also given. So we can use that. So the person who had done that, he has actually written that an inverse exists and he has given the inverse, but he has said that it's not a feed forward inverse because it is of the form, what was it? D over 1 plus d square, 1 over 1 plus d square, right? So what do you get? G of d this times this. What will you get? It will be d over 1 plus d square into 1 plus d square, which is d plus product of these two terms. 1 over d square into 1 plus d square plus d cube. But we saw that 1 plus d square plus d cube by divided by 1 plus d square is nothing but d plus 1, the quotient. So this. So we'll get d plus, which is nothing but 1. So an inverse does exist, right? But this is not a feed forward inverse because it has terms in the powers of d in the denominator. So we'll have to use a feedback to get that type of expression. We saw in the previous question, it's all connected. We saw here, right, in the realization. So there were only these forward connections, but I told you that even here also there might be backward connections that are given as feedback. So since we are solving on feed forward type of question, I did not write those. And in place of F zeros in the feedback connections, there will be Qs, Q1, Q2, up to Qm. But to do that, you should know the inverse. But that is actually, I mean, you might not be able to guess the inverse directly from G of D. So this is the proper method you should follow. Find the GCD of the two expressions, and then if the GCD is the power of D, then there does exist a feed forward encoded inverse. Otherwise, it doesn't exist. So for this question, the answer is no. Now we know that it is easy to answer the next question. We didn't get d power L for any of the first two options. We only got it for the third option. So 1 plus d square, 1 plus d square into 1 is d, which is of the form d power L. So the feed forward encoder does exist. And one more thing here is minimum delay feed forward inverse. So I don't remember exactly what the definition is for a minimum delay, what they mean exactly by minimum delay, but if I had to take a guess, then these are delay elements. So let's say there existed some other form from D power something else that was also an inverse. So you multiply this with this and get some other power of D that will also be an inverse, but this has some D power of something else. Since this one is nothing but D power zero, right? So that means there's no delay at all in this. So delay is zero. So I think that's what they mean by minimum delay. So the least power of D should be there, but I'm not sure of the exact definition for minimum delay feed forward inverse. But the other two are not inverses at all, and we have found an inverse. So a minimum among those should exist. From that itself, you can see that one should be the minimum delay feed forward inverse. Okay, only two more questions left. Question 9, or is it? Is it 3? Okay, we have 3 questions left. We are in question 8. So there's an image. Trellis is here. Let me get the image. What is going on, man? Nothing is working today. Give me a second, I'll get the image and we'll continue. Okay, I finally got the image. What is going on today? So many issues. Anyway, we'll move on. The figure given below is a trellis diagram of a 312 convolutional encoder. What is the correct expression for forward recursion alpha calculation? Notations are as used in the lecture, and you have the trellis here. Okay, so we have very less time left. So I'll just do this quickly. We have this from the lecture alpha L of L plus 1 of S is gamma L of S dash comma S, alpha L of S dash, where S dash is in the set sigma L, and sigma L is the set of all states at time L. This is Victor B encoding. Oh, this is BCGR. Okay, so that you can. Okay, so you can refer to lecture slide 10 for this formula. So derivation for that formula is given in that lecture. Okay. You don't have time to explain how we get that. That would mean alpha L. So in the options, they're asking for alpha L of 0, 1. So you have S is equal to 0, 1. So what are the states? Okay, so here your this gamma L of S dash comma S is a function of the state transition from the state S dash to the state S, and alpha L of S dash is in the state S dash. So alpha L of 0, 1 from the trellis diagram. So we see that 1, 1 and 1, 0 are going to 0, 1, right? So it will be S dash can be 1, 0 or 1, 1. So alpha L of 0, 1 is gamma. This is alpha L plus 1 here. So alpha L of S will be summation S dash belong to sigma n minus 1 gamma L minus 1 of S dash comma S gamma L minus 1 of S dash. So alpha L of 0, 1 will be gamma L minus 1 of, so S dash can be 1, 0 or 0, 1. So if we take 1, 0, then the gamma of the transition 1, 0 to 0, 1 times alpha of the state 1, 0 plus, so it's the summation over all S dash in uh, sigma L, so sigma L minus 1. So gamma L minus 1 of the other possibility for S dash is 1, 1 times alpha of 1, 1. Okay. Okay. Question 9 uses the same diagram. For 9 you have for the same encoder, same encoder in question 8. Um, they want the expression for beta. So you can see Refer to slide 11. You have beta L of S dash is summation over all sigma L plus 1 beta L plus 1 of S gamma L of S dash comma S. So again here sigma L plus 1 is the set of all states at time L plus 1, and here if you there are options. If you look at the options, you have S dash is 0, 1. So from 0, 1, you're going to 1, 0 or 0, 0, right? So those are the two states in L plus 1. So sigma L plus 1 is 1, 0 and 0, 0. So you will get beta L of 0, 1 is gamma L of 0, 1, comma. So S could be here either 1, 0 or 0, 0, right? 1, 0 or 0, 0 for the state. So first term, let's say it as 1, 0, gamma L of 0, 1, comma 1, 0 into beta L plus 1 of 1, 0 plus gamma L of 0, 1, comma 1, 1 beta L plus 1 of 1, 1. So that will be the recursion formula for beta. Final question, same for the same encoder in question 8. Give the expression for APP for that. Refer to slide 8 as they have given the formula for this. So L of UL is log of summation S dash to S over all transitions belonging to the set sigma L plus. So this set sigma L plus is the set of all these pairs of S dash and S, pair of states, such that when you transition from the state S dash to S, uh, if you give an input bit of 1. So if you go from state S dash to S, when your input bit is 1, then that pair S dash S belongs to the set sigma L. So over all such state pairs, probability of SL is equal to S dash, SL plus 1 is equal to S, comma R divided by summation s dash comma s belonging to sigma L minus. So these are all the state transitions that happen when your input bit UL is -1. By that I mean, since you're using bits, it's a 0. So P of SL equal to S dash SL plus 1. So the joint probability that that state transitions happens and that you receive the vector R. So received word is R. So that's the formula for APP. And again, you can further write this joint probability. You can split it up. So this is the joint probability that you receive the word R, the vector R. You are in the state S dash and you go to the state S. So this probability that you receive the word R can be further split into probability that you receive RT less than L, which is the part before time L of the received vector, and RL and RT greater than L. So this is the part you receive at time L, and this is the part that you receive T greater than L. And you do a bunch of mathematical manipulation that's given in the lecture itself. You will end up with RT greater than L given as P of S comma RL given as dash into P of S dash comma RT less than L. So what this means is, what is the probability that you are in the state S dash and you have received the vector RT less than. So let's say R was 1 0 1 0 1 1 1, and at time L you are here. This is at time L. So T less than L you received 1 0 1. At T is equal to L you received 0. At T greater than L you received 1 1 1. Suppose at L you are in the uh, state 0 0, and next you went to the state 1 1. So this would mean product of probability that you are in state 0 0 and you had received 1 0 1 into the probability that you go to state 1 1 and you receive 0, given that you were previously in the state 0 0 and you had received 1 0 1, into the probability that you get the vector 1 1 1, given that you are currently in the state 1 1. So that will give you the total joint probability that you're in state 0 0, you go to state 1 1 and you receive the vector 1 0 1 0 1 triple 1. So that's what it means. So here your P of S dash comma RT less than L will be alpha L of S dash. P of S comma RL given S dash will be the gamma L of S dash comma S, and beta L plus 1 of S. We saw this sorry, we saw alpha, beta, and gamma in the previous questions. So this is how you get them. P of RT greater than L given S is your beta L plus 1 of S. So your P of S dash S comma R is equal to alpha L of S dash, gamma L of S dash comma S, and beta L plus 1 of S. Okay. I hope you are following what I'm saying. Now you have to calculate this P of S dash comma S comma R for all these state transitions S dash to S at time L, right? Uh, and the received vector will be these. Uh, this is what you will receive. So what you received, right? And this is your input bit UL. So you have to check which of these transitions. Okay, so you have to substitute S and S dash from those state transitions that you have in the trellis. And what else? Find out beta L plus 1 of S for each of those states, then alpha L of S dash, gamma L of S dash, comma S. And finally, you have to substitute that. You have to find out which state transitions belonging to sigma L plus and which state transitions belong to sigma L minus. What is that formula? Here. So which state transitions belonging to this set and which state transition belong to that set. And for each of those state transitions, you have to evaluate P by calculating alpha, gamma, and beta. Then for all the state transitions belonging to sigma L minus, you have to calculate P again by finding out alpha, gamma, and beta. So if you write that in terms of alpha, gamma, and beta itself, then you will be left with alpha. Okay, this is a huge formula, so I'll try to squeeze it here. Log of. So in the numerator, the transitions that you have are in state 0, 0, transition to 1, 0, plus state 0, 1, transition to state 1, 0, plus alpha L of 1, 0, finally 1, 1. So if you look at so what are these states? In sigma L, the states are those for which the input bit is 1, right? And sigma L minus are those transitions for which the input bit is minus 1, which is 0, right? So let's look at the trellis here. Let me copy this trellis here so you can check that I'm not writing some hogwash. So we are at time L, right? So sigma L is all those transitions at time L for the input bit 1. So what are those transitions? You have one here, right? You have a one here, and a one here. So four transitions. What are those transitions? You are going from 0, 0 to 1, 0. You are going from 0, 1 to 1, 0. You're going from 1, 0 to 0, 1. And you are going from 1, 1 to 0, 1. So 0, 0 to 1, 0. That's the first term. Then 0, 1 to 1, 0. That's the second term. Then 1, 0 to 0, 1. 1, 0 to 0, 1. That's the third term. So the transition will be the argument of this gamma function. So 1, 0 to 0, 1 you're going, right? And 1, 1 to 0, 1. So the final term is 1, 1 to 0, 1, right? Then this is divided by the joint probability P, sum of the joint probability over all states, sigma L minus. The sigma L minus are those transitions at time L for the input equal to -1. Here it will be 0. -1 means bit 0. So those are which transmissions? Those transmissions are 1, 1 to 1, 1, 1, 0 to 1, 1, 0, 1 to 0, 0, and 0, 0 to 0, 0. So you will get alpha L of 0, 0, gamma L of 0, 0 to 0, 0. That's one transition, plus alpha L of 0, 1, gamma L of 0, 1 to 0, 0 is another transmission to beta. Third term, so third transition 1, 0 to 1, 1. Final transition 1, 1 to 1, 1. Okay. So what I did is actually, it's not, it looks big, but it's not complicated. You have this formula L of UL, which is the log of a ratio. The numerator is the sum of joint probability of a certain set of transitions. Denominator the sum of joint probability of a certain set of transitions. The set of transitions in the numerator are those transitions at time L where the input bit is a 1. In the denominator, you have those transmissions at time L where the input bit is a 0. And each of those p's can be written in terms of alpha, beta, and gamma as a product of alpha L of S dash, gamma L of S dash, comma S, beta L plus 1 of S, where S dash is the state you are in at time L, and S is the state you go to at time L plus 1. Okay, and you write that out, you will get an expression of this form. All right, that's it for today's session. Took too long due to technical difficulties. My internet connection was bad. I'll meet you next week.